Alright, I got some questions about when to use balance equations and when to use other equations for birth-death processes. So I'm going to try to address these. So first of all, the service rates. Let's look at those. If you have more than one server, let's assume that the single server's service rate is the same for all of our servers. So let's say 3 bank tellers or 2 bank tellers. Let's stick with 2 servers for now. If we have one customer in service, so we're in state 1, then our service rate is just going to be mu1. It's going to be whatever the service rate is for one customer. And if we assume that each of the servers has the same service rate of just mu, then the service rate when there's only one customer in service is just mu. Okay, now let's say we are in state 2, so we have 2 customers in the system. Well, now we have 2 servers working, so they're going twice as fast. So our service rate is mu2. And now if they work at the same speed, then here our service rate is mu, here it's 2 mu. If you have 3 customers in the system, but you still only have 2 servers, now you've got 1 in the queue and 2 still in service. So you still have a service rate of 2 times mu, whatever the single service rate is, which is the same as it is here. So that's where you need to pay attention to what's actually going on in the problem. Now, if you have an external process generating arrivals, then your lambdas are all going to be the same if they're coming from the same process. Cases where you would have different numbers of lambdas would be things like if the state were, say, the number of machines that were broken in a system. When you have 3 machines, they're breaking 3 times as fast as when you only have 1 machine working, say. So that's where that comes in. All right, now let's assume those dashed arrows are not there. So let's say we have a finite size queue, which means, or finite size system, which means either we have a capacity limitation on the queue or we have a finite population. So that would be things like the 3 machines problem, or if we only have so many people that could be, or customers that could be coming into the system. Now, if it's a closed system like that, where it's not an infinite queue, that's where it's easier a lot of the time to use this balance equations. So to set those up, we're using out equals in, flow equations. So lambda, starting with state 0, if lambda is your arrival rate when you're in state 0, your flow out of state 0 is just going to be lambda naught times p naught, which is the long-term probability of being in state 0, of having 0 in the system. And that's going to be equal to your flow in, which is going to be mu1, which is your service rate coming from state 1, times the long-run probability of being in state 1. So that's p1. So that's how we get the first equation. For state 1, same idea. Out, you've got this exponentially distributed rate plus that one. We're talking Markovian here. So that gives you this term here. And then flowing into state 1, you've got lambda naught p naught plus mu2 p2. So at that point, now what we're going to do is we're going to take this equation and we're going to state it in terms of, we're going to state p2 in terms of p naught. Why do we do that? Because of total probability. Because at the end, if we can get all of these equations in terms of p naught, then we can solve for p naught and then the rest of it will fall out. So from here, we're going to say this is going to give us that p naught, or p1 is equal to lambda naught over mu1 p naught, and that's p1. So now here we can take lambda 1 plus mu1 times p1, which is lambda naught over mu1 times p naught, and that's going to be equal to this. Okay, now we want to solve for p2. So we're going to subtract this off. So I'm going to do a little bit of manipulation there. So now I'm subtracting that from that side. And then I can group these terms. So I'm going to take that, multiply this guy times mu1 over mu1. And this whole thing is times p naught. Okay, just doing algebra. And I'm going to take that mu2 and divide this side by mu2. So now I have p2 on its own on the right side. And when I condense this thing down, well, let's see, I've got all over mu1, I've got lambda 1 times lambda naught plus mu1 times lambda naught minus mu1 times lambda naught. So these two terms are actually going to go away. And I'm going to be left with lambda naught times lambda 1 over mu1 times mu2 times p naught. And if those values are the same, if lambda naught is equal to lambda 1 and mu1 is equal to mu2, then this is just lambda squared over mu squared. So that's where I get to this result right here. So this is going to hold whether or not the Q is finite, but in the cases of the finite system, the nice thing is that at the end, you can add up. In this case, it's going to be P naught plus P1 plus P2 plus P3 equals 1, and you can add those up and you can solve for P naught. So you're going to plug in your terms in terms of P1, P2, or your terms for P1 in terms of P naught, P2 in terms of P naught, so that's going to go in here, and your term for P3 in terms of P naught, and just solve for P naught. Okay, so that's how you can get that probability, and you'd just be plugging in your values for your lambdas and your mu's. Now, this over here still applies, but because if you have an infinite number of states, solving for P1 or Pn is a little bit harder to do since it has to converge, and you need to use your series. So the nice thing is that to get your L values, your L, your LQ, your W, WQ, the math has been done already. So all you got to do, assuming that all of your mu's and your lambdas are consistent, is plug into this set of equations. If they're not, we have to use different models, and these are all in the notes. So that's what you do when you have an infinite Q. You can use your balance equations fairly easily when you have a finite Q, as long as it's not too terribly long. With this, you can also use, when you have a reasonable number of pi of states of n's. Here you can get L from your weighted average of your state. So it's just going to be the sum of the number of customers in the system in each state times the limiting probability of being in that state. That's going to give you L. And then here, LQ is it just accounts for S servers. So you take the Q length and you sum the same weighted average, but only for the Q, not for all of the servers as well. And then you follow through the rest of the equations there. So what you need to look at is whether or not your Q is finite or your population is finite. If it is, you can apply balance equations, and you can use these guys and then use your total probability and solve for P naught, and then do the rest of the math to get the rest of the terms, and you can use those and your weighted averages to get your LLQ and so forth. And if it's an infinite Q, then you can use this set of equations down here.